Hey guys, we are starting another new unit here, Unit 7. We're talking about exponential growth. So you saw a little bit of a preview of exponentials in Unit 6, and we're going to go more in depth with them in Unit 7. Before we really get into the exponential stuff, I want to do a quick review of function notation. So here is the equation of a line. Y equals 3x plus 4, y equals mx plus b. You guys are used to that. You used that in junior high. You've seen that a million times. And then if you remember in the first Unit 4, we started using f of x instead of y. Remember, that's how you say it, f of x. It's not f parenthesis x or f times x. It's f of x. That's how you say it. So all it does is it takes your y out and replaces it with f of x. Again, it does not mean times x. Instead, what it's doing is it allows us to describe what we are substituting into an equation. So if we have a problem like this, what does f of 2 mean? It means we're going to take the original equation and substitute in a 2. And f of 2 is just good notation because now instead of having y equals, we have f of 2 equals, so we know exactly what we substituted in. So the other side of my equation is 3x plus 4, but anywhere I see an x, I'm substituting in a 2. So that gives me 6 plus 4, and then that gives me 10. So f of 2 equals 10, that is my answer, and that means if you take your function f, you substitute 2 in, you will get 10 out. So 2 is the input, 10 is the output, f was the name of the function we used. If I write f of 5, that means plug in a 5 to the x. So I had my equation, my function 3x plus 4, but I'm going to plug a 5 in for my x. So f of 5 equals 15 plus 4, and then f of 5 equals 19. Okay, so just a reminder on function notation and what it is. It's just kind of a fancy notation for substitution. All right, so we're talking about exponential growth here, and a lot of times students ask, when am I ever going to use this? Exponential functions is used in many different areas, and here's just a few I named. You might have done half-life in science class with different chemicals and things. This is going to be the next section, exponential decay. Depreciation is decay, but they're all exponentials. Okay, so growth and decay are just, are you increasing or decreasing? All right, graph f of x equals 3x plus 1. Well, I know I would start at my y-intercept, which is 1, and then my slope is 3 over 1, so I would go up 3 units to the right 1. Up 3 units to the right 1. Okay, and I can go ahead and draw in my line. Oh, that wasn't terrible. Okay, what is the change in y value for every x? What is the change in y value for every x? So for every x, it's already over 1. Well, the y value is going, well, let's say an increase. 3 units. Okay, in other words, you are adding 3. So you know from Unit 6 that this would be an arithmetic sequence that we would be talking about. Down here, graph f of x equals 3 to the x. So let's make a t-chart since that's not in slope-intercept form. If we plug in 0, 3 to the 0 power, if you don't know that rule, anything to the 0 power is 1. So 0, 1. We plug in 1, 3 to the first power is 3. Plug in 2, 3 to the second power is 9. Okay, well that's weird. It's definitely not a straight line, right? Okay, I could not connect these and make a straight line. That would have a big bend in it. This is actually going to look something like, this is not the best version of it, something like this. It should probably be more like this. Ah, I missed it. Something like that, though. It's definitely a curve. Okay, what's the change in y value for every x? Well, my first one went up 1, 2. My second one went up 1, 2, 3, 4, 5, 6. So I don't want to talk about adding because it's not adding the same number. But just like in the last unit, I can talk about multiplying. What I'm doing here is I'm multiplying by 3. Multiplying by 3. So I'm going to write that down. And hopefully you're recognizing that that would be a geometric sequence. So we said already that this was arithmetic and this was geometric. Remember, arithmetic always deals with adding. Geometric always deals with multiplying. Also, if you remember, I would ask you to describe what the graph was doing. Here, we would know this would be a linear graph, arithmetic, linear. Geometric, we learned, is exponential. So there is your connection between units 6 and unit 7. So we're going to focus on exponentials. Keep in mind your graphs are curves. They should not be straight lines. If you are graphing a straight line and you're talking about something exponential, you're graphing it wrong. So if you're looking at a function, how do you determine if it's linear, exponential, or neither? Which of these is linear? You should be able to pick that one out. Okay, there's one of each here. Which one's linear? Hopefully you're looking at this one. Okay, when we're talking about linear, we generally are talking about y equals mx plus b. In this case, we have that. It's just we have some different variables. Instead of y, we have f of t. Our m is 6. Our x isn't an x, it's a t. Ooh, but I don't see a plus b, so that means it was plus 0. So things that are linear are always, they always have a variable with an exponent of just 1. In other words, no exponent shown. So then which of these is exponential? Both of these have exponents, but only one of them is exponential. The kind of key trick to remember it, the letter x in the word exponential, there has to be an x or some other variable in the exponent. So which of these two functions has a variable in the exponent? Number 5. Okay, so you have to have an exponent, and the exponent has to be a variable. To be exponential, I'm going to type that out, must have an exponent that is a variable. That's how you can tell if something is exponential. There you go. This one has an exponent, which means it can't be linear, but the exponent is not a variable, which makes that neither. Okay, so those tests again. To be linear, has to be to the first power. Nothing crazy going on. We've already done that in one of the past units. To be exponential, you have to have an exponent that is a variable. And if it's anything else, then it's neither. Okay, so any exponent other than a variable. Standard form of an exponential equation is y equals a times b to the x. The a, label that your initial value. So that's how much is happening at the beginning of your situation, or generally when your time is equal to 0, whether it's when 0 months, 0 years, 0 whatever, at the beginning of the time. I'm sure you do. No, it's okay. No. For the B, that is your growth factor, and that is how much you're growing by. Maybe you're doubling, maybe you're tripling, then it'd be a 2 or a 3. Okay? All right, so let's look at one. Sketch the graph by filling out a t-chart. Find at least 3 points, even if they're not all going to fit on the graph. So our initial value here is 2. So that's going to tell you that if your x is 0, your y value is 2. Check that if you're not sure about it. I would be doing y equals 2 times 4 to the 0. And remember I said anything to the 0 power is 1. That 0 is on the 4, so that becomes 1. 2 times 1 is 2. Okay, so you can do this math to figure that out, or you can always recognize that if you're in the form y equals ab to the x, that a is always going to go with an x value of 0. Okay, do a couple more. If you plug 1 in, 2 times 4 to the first power is just 2 times 4, which is 8. If you do 2 times 4 to the second power, well, 4 squared is 16. 16 times 2 is 32. So you can see why they're not really all going to fit on there because these numbers can get big very quickly. That's what exponential functions do. Okay, so plotting these, 0, and I'm just counting by ones here, so I can label that's what I'm doing. 0, 2, 1, 8, 8, and obviously 232 is going to be off there. Okay, what I do not want to see you do though, well, I don't want you to miss all your points, but I don't want you to just draw a straight line because we know this is not a linear function. We know it's exponential. So you need to make it look like an exponential graph. An exponential graph has a curve, okay? So this is obviously curving upwards, and it's going to kind of bend here, hit that point. I'm going to move it and make it hit it better. Okay, and then it flattens out. So mine kind of looks like it starts going up, but it shouldn't. It should flatten out. All right, so even if you can't plot all your points, it still needs to take the form, should be more like this, and then kind of straighten out a bit. It needs to take the form of an exponential. So even if all your points aren't fitting on there, you have to make it look like an exponential graph. If it looks linear, you will not get credit for it. All right, next one. I'm going to bust out a calculator here. You can do the initial value definitely without a calculator, right? So when your x value is 0, okay. Wow. You're complaining. These students are whiners. Okay, so your initial value is 0.6, which you can pull right out of the equation. I'm recording. So if you don't see that, though, you can definitely calculate it. So you would just do 0.6 times 1.5 to the, oh, I don't want to square it. Ooh, I don't know how to use this. Let's try it this way. 0.6 times 1.5 to the, that's what I needed, 0 power. And look, it's 0.6. Okay, so I want you guys to actually do, let's do 6. Go 0, 1, 2, 3, 4, 5, 6, and fill these numbers in. Okay, so there's all my points, and I am again going to count by ones. And I'm just going to plot these 0.6. Good morning. 1, 0.9, 2, 1.35, 3, 2.025, 4, 3.04, 5, 1, 2, 3, 4 and a half, and 6, 6.8. Thank you. And then go ahead and draw in your curve. That's very hard to draw on here, I apologize. Okay, and then it's just going to kind of flatten out. So that's what your linear graphs look like. You can also check these out in your calculator. Please do. Do little typing in of some different exponentials, and you know how to graph in your calculator. Should be no problem at this point. Given the following table of values, create an equation that fits these points. Well, we know, first of all, I shouldn't go straight to that. We want to look first and see if we're really exponential. Could we be linear? What are we going? Well, from here to here, we're adding 3.2, but we're certainly not adding 3.2 here. So we don't want to go with addition. So if we know it's not adding, the next thing we would want to try and do is multiply. Well, I don't know what number 2 times what is going to give me 5.2. So instead of trying to go that way, work backwards. Do some division. 5.2 divided by 2, hit up a calculator, it's 2.6. So that means 2 times 2.6 should give me 5.2. Check that out. Does it work? Yep. 5.2 times 2.6 is 13.52. So yep, that works as well. Okay, and you can check it. It'll work here as well. Okay, so we know we're multiplying by 2.6. Think about the things that you know then. If you are multiplying, you know it's exponential, so you're working in the form a times b to the x. A is your initial value. Your initial value occurs when your x is 0. By the way, don't always think it's just going to be your first point, because they could have given you, started with negatives for your x value. So you got to look when x is 0, what's your y? That's your initial value, so 2. Your b is 2.6, right? That's what your growth factor is. That's what you're multiplying by each time. And x is just x. So that is how you come up with your equation. Okay, so now we're working with percent increase. So sometimes we just have a growth factor. and sometimes you use a percent increase. This is still your growth factor. It's just if they've given you a percent, this is how you find your growth factor. It's 1 plus your percent increase. And a quick explanation of that. If you're saying something increases by 50%, so say we have, oh, I don't know, $100, and we're saying it increases by 50%. That's not $50. Oops, that's not a dollar sign. That would not be $50. That would be less. There would be no increase. To make it increase, you have to add 1 to it because you need 100% of your original money, your $100, plus the $50 of the 50% increase. So you always want to add 1, and that just accounts for your initial amount, 100% of your initial amount. Okay, hopefully that all makes sense. Your percent must be converted to a decimal though. So keep in mind how you change percents to decimals. So if you have 25%, to turn that into a decimal, your decimal's here, you have to move it 2 spots to the left. So 25% is the same as 0.25. Percent means per 100. So it makes sense 2 spots moving it because that's multiplying or dividing by 100. What if your percent were 1.3%? You still need to move it 2 spots. So now it becomes 0.013. Okay, what if your percent is 0.2%? So you might be like, oh, well, that already is a decimal, but it's not. It's a percent still. You still have to get rid of your percent sign by moving this 2 spots. So 0.2% is actually 0.002. Okay, so I always just make these little curves, and I know I have to fill zeros in there. So please make sure you are not putting the percent in there. You have to change it to a decimal. Okay, for each problem, create an equation and model a scenario. A Lego set is worth 100% or $100 and increases by 23% each year. Well, that definitely means it is exponential. Your initial value is $100, and your B is going to be 1 plus your percent, but your percent has to be written as a decimal. So 0.23, you've got to move that over to the X. So Y equals 100 times 1.23 to the X. Hi. You guys go ahead and try the next 2. Pause the video and do it now. Okay, check your answers. Definitely check and make sure you have the right percents. So 1.5%, you had to move that decimal 2 spots to the left, which makes it 0.015, and then add your 1. For 205%, your decimal's here. You need to move it 2 spots over, which makes it 2.05. So check your answers, make sure you've got them right. For each equation, identify the initial value and the percent increase. So you're in the form y equals a times b to the x. Your initial value is just that number right there. So that means you have an ordered pair at 0, 6. But that's your initial value, 6. Whoops. Okay, and then this number, remember, represents 1 plus your percent. So 1 plus your percent, that means the 1 right here can go away. You subtract 1 off, you're left with 0.516. But that's not your percent increase. That's already been changed into a decimal. So to change into a decimal, you moved it 2 spots to the left. To get it out of a decimal, you need to move it 2 spots to the right. So that makes it 51.6%. You guys go ahead and try the second one. Okay, so initial value, it's in y equals a times b to the x, is -8. Your percent increase, so 1 plus your percent is 3.2. So that means your percent by itself is 2.2. But again, that's already been converted to a decimal. So you need to get it back into percent form, so you're moving it to the right. So this is 220%. So to go from percent to decimal, you move 2 spots to the left. To go from decimal to percent, you move 2 spots to the right. So make sure you're doing those in the right direction. Okay, and last thing, I want you guys to watch this video. It's only a couple minutes long. It's a nice little YouTube video. I actually saw it pop up in BuzzFeed in my Facebook timeline the other day, so it's super popular these days. Hopefully you guys can hear the sound on this. I don't even know. Actually, I'm not going to do this because I don't think you guys are going to be able to hear the sound. I instead am going to post the link and I want you guys to go to it. So I will post the link on the um, website under this video, and I want you to go ahead and watch it. It's about folding paper and how many times you would have to fold a paper to get to the moon. And then after that, I want you to maybe do a little investigation. How many times can you actually fold a piece of paper? Either Google it or try it. It's kind of interesting. All right, watch this video posted underneath this video.